speaker is Karina Koval from Heidelberg.
So thank you for the introduction and for the invitation. I'm really happy to talk about some of our recent work here. And what I want to talk about is how transport maps can be used for scalable sequential design for Bayesian inverse problems. So this is joint work with Qiangrang Cui, Roland Herzog, and Robert Scheichel. So I first want to motivate the type of sequential design problems we're interested in, because they're a bit different from the ones we've seen in some previous talks. And I'll do this using a few motivating examples, some of which I'll get back to towards the end of my talk. So many models describing real-world phenomena involve unknown or unobservable inputs. And if you want to make accurate simulation using these models, or accurate prediction about these systems, you need to have some knowledge about these unknowns. So just to give one example, if you want to monitor the quality of water flowing through some aquifer, you have to have a pretty good idea of the physical properties of that aquifer, like its permeability field. And this is not something you can observe directly, but you can observe some related quantities, like the water head pressure, at some wells that have been drilled into the ground. And another example is related to medical imaging, where you want to infer various properties of the tissue, determine whether some tissue is cancerous or not, and all you have access to are some related measurements somewhere along the boundary of your domain. And in both of these examples, you can use your data as well as the mathematical model to infer your unknown parameter. An accurate estimation relies on having access to the quality and a large amount of data. Unfortunately, in reality, data is often sparse and corrupted by noise and expensive to obtain. And that's where the optimal experimental design, or OED, problem comes in. So given our limited resources, how should we acquire data to optimally estimate our unknown parameters? So where should we drill our wells, or where should we illuminate our object in medical imaging? And here I'm particularly interested in the sequential design of experiments. So in sequential OED, your designs are chosen in sequence, indexed by distinct stages, where at each stage, the results of all your previous experiments are used to guide the current design. So there's a sort of feedback loop in the optimization procedure, and what this might look like in the medical imaging setting, for example. Maybe a priori, you know you're going to find some blob of tissue somewhere in your domain, but it could be absolutely anywhere. So given this state of knowledge, it kind of makes sense to measure somewhere in the middle of the boundary of your domain. But let's say you conduct that experiment, and the data suggests actually this blob of tissue is going to be somewhere in the upper right-hand corner of the domain. So given this updated state of knowledge, you can now better target your designs towards this ground truth. And these are the problems we were interested in, and in particular, we wanted to develop methodology for SOED for problems involving non-Gaussian posteriors. So we're dealing with nonlinear parameter to observable maps, and we're also dealing with computationally intensive models. So applying the parameter to observable map in our examples is going to require solving a PDE or even systems of PDEs. And we're also dealing with a large number of unknown parameters. Our unknowns are going to be discretized functional inputs into our PDEs. So before I get into our approach for this, I first need to introduce some notation and some mathematical tools. And we first need to solve the inverse problem. And of course, here we're going to take a Bayesian approach to doing this. So here, this little orange M is going to be our vector of unknown parameters. And it's related to our data D via this parameter to observable map F. So F is where your PDE solves come in. And this parameter to observable map can also depend on this design. So here, this little blue E vector is going to be our vector of design parameters. It can be, for example, the spatial coordinates at which you're going to drill your wells in this groundwater quality control example. And in the Bayesian approach, you need some sort of prior distribution, for example, a Gaussian on your parameters, and some sort of noise model. Here we take additive Gaussian noise, and the design can also modify this noise term, for example, through the noise covariance. And then our solution to the Bayesian inverse problem can be obtained via Bayes' rule, right? It's this conditional distribution And it's design dependent, proportional to the likelihood times the prior, and the design enters in through the likelihood. And here we're eventually going to be interested in sequential design, so we also need some way to characterize our sequence of posteriors. So we're going to do this by solving an inverse problem in each experimental stage. And here's the model for this stage K inverse problem. We still have our parameter to observable map and noise model. It's just now the parameter to observable map and noise can vary in between experimental stages. And at stage K, we've already observed K-1 sets of data. So our current state of knowledge, our stage K prior, is actually our previous stage K-1 posterior. So here I've introduced this experiment history vector. And Bayes' rule once again allows us to update between adjacent posteriors. Our stage K posterior is still proportional to this design-dependent likelihood. It's just now our stage K prior is the previous posterior. So that's how we deal with the inverse problem, and now we're ready to get into the actual optimal experimental design. So recall, we want to find experimental conditions that lead to the most informative data in each experimental stage. But what do we actually mean by design? So for the purposes of this talk, we're going to focus on subset sensor selection problems. So in these problems, you typically assume you can measure some function of the state, so of the solution to your PDE, at a small number of locations. So you assign a candidate set of locations, and at each of these locations you assign a binary weight. So this weight acts like an on and off switch. If the weight at location xj is 0, then you're not going to place a sensor at that location, and if it's 1, then you will. And your design goal here for these problems is to now choose a subset of sensors from this larger candidate set. And the nice thing about these sensor selection problems is that it's rather straightforward to define how the design enters into the inverse problem. It enters via this binary weight matrix. So this is a rectangular matrix. The number of rows correspond to the number of chosen sensors, and the number of columns to the number of candidates that you have. So this weight matrix essentially is a row or column subset selection matrix. And it enters through the likelihood by modifying this inverse noise covariance term here. So that's what we mean by design, but what do we mean by optimal? So in Bayesian inverse problems, our typical goal is to find designs that minimize our level of uncertainty in the posterior. So we want to find designs that lead to the tightest posteriors possible. And here we're going to take a greedy or myopic approach to sequential optimal experimental design. So at each experimental stage, we're only aware of the previous experiments. We're not aware that we're going to make more experiments in the future. And this is a suboptimal approach to sequential design. However, it does have its advantages if you don't have a hard limit on the number of experiments you're going to perform. And you can also get immediate feedback as to how well you're doing after each experiment is conducted. So this is what we're going to do, and we're going to define our optimal design in each stage as that maximizing this incremental expected information gain. So we want to find designs that maximize the KL divergence between adjacent posteriors on average for all possible realizations of the data. And this is a computationally challenging quantity to optimize, and the main reason for that is because this incremental expected information gain is a very complicated function of intractable densities. So you need to take expectations with respect to intractable densities, and you also need to evaluate these densities at different points. So just to make that a little bit more clear, after the first stage, both your posterior and prior are no longer tractable and high dimensional. You don't have a closed form expression for the KL divergence, nor its expectation. So you need to employ some sort of numerical approximation, Monte Carlo, nested Monte Carlo. But this is going to require a large amount of samples. So in other words, a large amount of PDE solves. And this is just to evaluate this EIG at one design point. In any sort of optimization procedure, you're obviously going to need to evaluate this at many different designs, and we want to do this over multiple stages. So this can get very computationally prohibitive very quickly. But in sequential design, we're often interested in computing these designs rather quickly. And the way that we're going to alleviate these challenges is by using transport maps. So transport maps allow you to define a coupling between different distributions. So if you can find a map T that allows you to transform samples U distributed according to a very simple reference density, just a standard multivariate Gaussian, to samples X distributed according to your target intractable density, then you can obviously obtain samples from this density, but also evaluate those evaluate the density at those samples via these push forward and pull back operators, which are just change of variables formulas. But how can these transport maps help us? So we're going to use them to define an easier to evaluate surrogate on the incremental expected information gain. So here we're on stage K, and assume we have a map Tk-1 that allows us to approximate the stage K prior. Using properties of the KL divergence, as well as recent results from this paper that I link here, we can bound the incremental expected information gain by this term, this log determinant of the identity, plus this H matrix that depends on the current design, as well as our transport map Tk-1. So this matrix H is an average Fisher information matrix, so you need to compute expectations with respect to your reference density, and you need access to the Jacobians of the parameter to observable map as well as the transport map. So you typically can't find a closed form expression for this, but you can approximate it using Monte Carlo, but the key is this approximation is much easier than if you were to approximate the incremental expected information gain itself. So we're going to use this surrogate or upper bound to guide our design selection. But how do we actually define and construct this transport map? So a key tool we're going to use is the Knuth-Rosenblatt or KR rearrangement. So this is a unique triangular order-preserving map. So what that means is that the kth component of this map depends only on the first parameters, x1 through xk, and it's strictly monotonically increasing in the last parameter, xk. So it's an invertible transformation. And of course, the triangular structure of these maps is computationally convenient for defining these push-forward and pull-back operators. But the key feature about these KR maps that make them particularly useful for sequential design and Bayesian inference is that the triangular structure exposes conditional densities. So through the kth component of this map, you actually have a way to approximate the conditional density of xk conditioned on x1 through xk-1. And one way to define these maps is actually via conditional cumulative distribution function, CDFs, of these conditional densities, xk conditioned on x1 through xk-1. And this is the way we're going to do this. We're going to define these transport maps or construct them via tensor train decomposition of the square root of the target density. So tensor trains just allow you to approximate a multivariable function as the product of matrix-valued univariable functions, these GIs here, which are sometimes referred to as the tensor train cores. And I have a visualization of what this tensor train looks like. So the kth matrix has Rk-1 rows and Rk columns, and the dimension of these matrices affects how accurate the approximation is. And of course, once you have an approximation to the square root of the target, you can obtain the approximation to the target density itself by just squaring. But the key feature about these tensor trains is that the separable form allows us to define and compute these conditional CDFs that we need to define this transport map. So we can now explicitly construct a map T that pushes forward the reference to our tensor train-based approximation to the target. So this is what we're going to do, and I don't want to talk about how these tensor trains are constructed, but there are efficient algorithms for doing so based on cross-interpolation methods. And the key features of these algorithms for the purposes of this talk. So first of all, you do need the ability to evaluate the unnormalized target density. Also, you do have some control over the approximation error with respect to the Hellinger distance through these tensor train ranks, which is quite nice. However, the number of evaluations of your unnormalized target, or the number of PDE solves required, scales linearly in the dimension of your variables, so in the dimension of x here, for example, and quadratically in the ranks. So what this means is that constructing these transport maps, particularly for approximating these high-dimensional posteriors, it can be quite costly. But remember, we want these designs quickly. So there's a few tricks that we need to use to make this feasible. And the first thing we're going to do is we're going to push the bulk of the computational cost, which is incurred during construction of these transport maps, into a sort of offline phase in each experimental stage. And the way we're going to do that is by using conditional transport. So at each stage, once we find our optimal design maximizing our upper bound, we're going to build this joint transport map, for example, using our tensor train-based procedure, and this map can be constructed while the experiments are conducted, so while we're actually waiting for new data to come in. And this joint map allows us to push forward a product form reference density to the stage K joint density. So this is the density on the stage K data and the parameters conditioned on all the previously conducted experiments and the new optimal design. And then once the experiment is conducted and we're given our new set of data, we can now immediately, using this triangular structure, define our transport map TK that allows us to approximate the new posterior or the next stages prior. And this part can be done without any additional PDE solves. So again, this allows us to push the bulk of the work into a sort of offline phase in each experimental stage. However, there's still a few issues. So first of all, the efficiency of the construction is strongly tied to the ranks R, right? We have this quadratic scaling in the ranks. And unfortunately, these ranks can get arbitrarily large for highly complicated densities, for example, those exhibiting highly nonlinear correlation structures or those that are concentrated to some subregion. And the way we're going to work around this is by using preconditioners. So what's the idea? If we can find a map R that allows us to transform our intractable target density into this intermediate density Q that is much closer to our reference, much closer to a Gaussian, then we can now focus all our attention in computing this intermediate map Q going between our reference to this easier to approximate intermediate density. But what R should we use? Obviously, the optimal R is the transport map T itself. But in sequential optimal design, we actually have a natural choice of preconditioners that we can use in each experimental stage. And the reason for that is because our consecutive posteriors are somewhat close to one another. So if we only measure a small amount of data at a time, what we can do is we can reuse the previously constructed transport map to define a preconditioner that simplifies the construction of the transport map for the stage K joint density. So given this previously constructed transport map, we define this new preconditioner that depends on the map, and we now define our transport map, our joint transport map of interest as the composition of this preconditioner, and this intermediate transport map, which is what we approximate. And this typically requires much lower ranks to approximate. So we've reduced the quadratic scaling here. However, there's still one computational issue, and that's that the number of PDE solves scales linearly with the dimension. And here, again, we're dealing with discretized functional inputs, so these can be thousands, tens of thousands, or even larger. So this is a significant scaling factor here. Luckily for us, in many Bayesian inverse problems, the data is often informative only on a low-dimensional subspace of the parameter space. So for example, you have your prior, you observe some data, and it constrains this prior only in a small amount of directions. And if you can find these directions, you can then decompose your parameter into a data-informed part and a data uninformed part. And likewise, decompose your posterior into a posterior restricted to this low-dimensional subspace and the prior in all the orthogonal directions, right? Because the data is not informative there. And one way to find these important directions is called this data-free likelihood-informed subspace approach. And in order to compute these directions, you just need to compute an SVD of an average Fisher information matrix. So again, you need access to the Jacobians. But how can this actually help us? So remember, at each stage, we want to approximate the stage K joint intermediate density. Well, it turns out we can find these data-free likelihood informed directions that are important to this intermediate density by computing the SVD of exactly the average Fisher information matrix that we've already computed in finding our optimal designs. And once we have these directions, we can likewise decompose our intermediate density into its low dimensional restriction and the prior everywhere else. And what this allows us to do is focus our computational effort on building this much lower dimensional map, this Q tilde that pushes forward some reference to our restriction to the low dimensional subspace. And then we can, of course, embed this into the large dimensional space of interest. And this really allows us to significantly reduce this linear scaling factor because the informed directions, especially if we're only observing a small amount of data at a time, are going to be relatively small and also typically independent of the discretization. So before I get into the numerical results, just to summarize the overall procedure. In each experimental stage, the first thing we do is we're given a new set of data, and using the previously constructed map, we can immediately define our transport map that can approximate the new prior, which we then plug into our surrogate, our upper bound, and we maximize to find our new optimal design. And we then construct our transport map, our next joint transport map, as the composition of this preconditioner and this intermediate transport map, which we can do efficiently by exploiting likelihood-informed subspaces. But of course, there's a few other tricks in there as well. So what does this actually look like in practice? So here I'm going back to my medical imaging example here. So this is actually an example of photoacoustic imaging, which is a hybrid imaging modality. So what that means is to apply the parameter to observable map, you actually have to solve two coupled PDEs. There's this optic PDE and an acoustic PDE. And what we infer for here is the absorption coefficient, which enters into the optic PDE in various different locations. And the two are coupled via this initial pressure here. And there were two designs we were interested in here. So first of all, the location of the light source, which enters as a boundary condition into the optic PDE. And we assume we can illuminate from the top or bottom of this rectangular domain that we're working with here. And the second design that we were interested in is choosing one sensor somewhere on the top or bottom boundary from some larger candidate set at which to evaluate the acoustic pressure at various different times. So our sequential goal was to now choose this optimal location as well as optimal illumination source in each stage for optimal inference of this absorption coefficient. And after discretization, this coefficient is roughly 4,000 dimensional. And we wanted to assess if our kind of designs maximizing the surrogate produce reasonable, good designs. And we also wanted to make sure it could adapt to different ground truths, right? Because we're interested in sequential inference here. So we tried it out on these two ground truth examples here. So first I have a visual comparison. So here I'm showing the posterior mean obtained after the first, third, and fifth experiments have been conducted for both ground truths, as well as the optimal designs that were chosen. And as you can see, the designs do tend to diverge after the first experiment is conducted, of course. But the key thing is already after 5 experiments have been conducted, we have a pretty good reconstruction of the ground truth here, right? So this does seem to suggest this surrogate is a valid surrogate. And we did more rigorous tests as well, of course. So what I'm visualizing here on the x-axis is the number of experiments that have been conducted for both ground truths. And on the y-axis is an accurate approximation of the incremental expected information gain. So our pink diamonds correspond to designs maximizing our upper bound, and the black dots correspond to randomly chosen designs. So as you can see, the pink diamonds do tend to outperform these randomly chosen designs rather consistently, just once again suggesting that kind of this easier to evaluate surrogate is a reasonable choice for guiding the data acquisition process. Okay, so those are the numerical results, and just to quickly summarize, so these sequential designs can be chosen using this easier to evaluate surrogate on the incremental expected information gain, which requires access to transport maps that can approximate our sequence of posteriors. And we could push much of the computational cost offline in each experimental stage using conditional transport. And the efficiency is further improved by using preconditioners at each stage and exploiting inherent low-rank structure for scalability purposes. And just a few remarks here. So I have focused on sequential OED in this talk. However, you can also use the surrogate, this upper bound on the IEIG for standard batch OED. And you can also use the ideas for sequential inference, right? As a byproduct of our approach, we actually have kind of the sequence of approximations to our posteriors. And so here I've also kind of motivated everything using these tensor train-based approximation to transport maps, but you can of course use other constructions of these transport maps, and I think they could still potentially benefit from preconditioners and these likelihood-informed subspaces. And I don't know how much time I have, I guess.
A couple of moments.
Okay. So there's obviously many further questions. So we haven't really explored theoretically how close to optimal designs maximizing this upper bound are, but it does seem to work well in practice. Of course, that's not a very satisfying answer. We did test it with more accurate approximations of the incremental expected information gain. Also, we've assumed that we can only measure a small amount of data at a time, but what can we do in the large data setting, right? Because then the data dimension is also very large. We can also reduce the dimension, again, using these likelihood-informed subspace ideas, but the problem here is that our adjacent posteriors are no longer close enough to one another, so we might need better preconditioners there. And we're also very interested in extending these approaches to density-free sequential optimal experimental design. For example, if you have some quantity of interest that you're interested in. And in these scenarios, you can't evaluate the prior nor the likelihood, but you can generate samples, and then you can use these sample loss-based approximations to these transport maps. And how can we do this efficiently and accurately? And with that, I want to thank you for your time. We do have a preprint available, and here are some references.
Yes, we have time for questions. I have one. So, about the greedy aspect of the strategy. Yeah. So, I guess you consider the non-myopic case, right?
Yes.
And where I want to go at is, did you think of what it converges to somehow? So I know you don't have really a
in the non-myopic case.
Even in the myopic case,
yes.
What would be the limiting behavior?
So I would imagine at some point, at least in kind of batch OED, at some point you start to see a saturation of information.
Yeah.
And I would imagine that would be the case in this sequential setting as well.
I imagine as well,
yeah.
But I think the kind of limiting thing will not be, would be some kind of posterior with respect to all the possible sensor locations.
Oh, yes.
See what I mean?
Yes.
Which
yes.
is not like perfect knowledge, but it's more like converging to some kind of best possible
yes.
posterior with respect to the available information.
Yes, yes.
Right?
I mean, because we're using this candidate set of locations, you mean?
Yes, exactly.
Yes, exactly.
Did you prove that?
Did I prove that?
Yeah.
No, no, I didn't.
And do you know what could be gained by doing non-myopic?
I mean, you're definitely going to get better designs. So in this myopic setting, you can certainly get into a situation where you perform some experiment and it gives you absolutely no knowledge whatsoever, and then your new posterior is pretty much the same as the previous prior. You maximize that, and you're kind of stuck in this one little location. So I do think it would be interesting to extend these to the non-myopic settings, but I think that would be very computationally challenging in these high-dimensional PDE-based scenarios.
I have a follow-up question that I want to check. Yeah.
Maybe I missed something. Thanks for the presentation. I would like to ask, how did you construct the transport map? Mm-hmm. So what kind of loss function you use to construct, because you have a non-normalized, unnormalized density function.
Right, so there's no loss-based construction for the transport map itself. So the key thing here is with these tensor train-based approaches, it's essentially a function interpolation problem that you're solving. So the key approximation comes in approximating your target density. And then once you have that, then you can compute these conditional CDFs analytically and define.
Then it's bijective because you are plotting the density and you need the CDF transform, like the integration, probability integral transform to go back to your
yes.
Yeah, go ahead. And then we can continue during the break.
Yes. So my question is exactly here, so it's quite fortunate. The way you pick the ranks, or the intermediate ranks of the tensor course, like how sensitive is the approximation of your high-dimensional, like in this case density, with respect to how you play around? Like, do you have to play around with it a lot, or do you say, oh, this is one core rank and I just go with it?
So there are algorithms that choose these ranks adaptively, so you can feed them in some tolerance, some error tolerance that you want them to satisfy, and in each kind of iteration they'll increase the ranks to kind of target this error tolerance that you've prescribed. But it is, there's not too much theory about how large these ranks need to get in order to kind of get these sufficiently accurate approximations. There is some theory for Gaussians in the correlated setting, but for general PDFs, I don't know.
So what basis did you pick to approximate the densities?
So these we're using second order Lagrange elements. Yeah.
Okay, thank you again.